overlap. And my understanding is that you may have done some component stuff in Physics 4B. So here we go. So let me do that overview one more time just to make sure that we're all speaking the same language here. Okay. And so ultimately, here's what we got to do. We have the differential equation approach. And this approach here typically lives in what is called the time domain. So what do I mean by this time domain? I mean the following two things here. You have a response, and because we're only looking at steady state, that goes to 0. Okay. And when I look at this guy, what we find here is that we solve, let's say, a second order differential equation. The solution must be in the following form. It must be b1 cosine omega t plus b2 sine omega t. To start moving this into the phasor form, what we do here is that there's this complicated way where I can take this b1 and b2 and then add a phase into a cosine function. And if you just read my notes, it shows you exactly how to do that. So ultimately, we're most interested in getting into this form, where now I have what they call a phase angle. And in Physics 4B, you must have talked about this phase angle at some point. I mean, whether you went into these details, it doesn't really matter. We will. So what we're going to do now is that this is a complicated way of doing the problem. So what we do then is we move into the complex plane. And when you do this mapping into the complex plane here, what we do here is that we now have what is called the frequency domain. And in the frequency domain, we have complex vectors that have a magnitude and a direction. So now, we're in this frequency domain. So if you see me write this language, I'm just separating these two here. And what you're going to see here, in this frequency domain, we now have a complex vector that has an amplitude, which I'll call Zn. And this guy here looks like Ej omega t plus theta. So you can see that this phase is exactly as that phase right there. Okay, sorry about that. And so when you do this, what you'll find here is that we kind of separate this thing out. And what I said last time, this is what they call a phasor. Okay? And you're going to see that this Ej omega t term always drops out. When you start doing the differential equations, you'll see that it always drops out. So when we go to calculate a phasor circuit, you'll see then that this will never pay attention to that guy. But we'll add it at the end. But how do I go from this form into that form? What we do then is that we do a transformation going backwards. And so what we do here is that now we solve the phasor circuit. Okay, we solve the phasor circuit and use Euler's relation to transform back into time domain. Right, so if I look at this guy, so now I'm going to take the real part of the vector like this, and when I take the real part of this, remember I'm taking the real part of this guy right here. So if I take the real part of this guy, it's going to be, right, so this will be cosine omega t plus theta plus j sine omega t plus theta. So all I did here is that I rewrote this guy using Euler's relationship, and if I take the real part of this, I actually get this guy right here. Oops. I get Zm cosine omega t plus theta. So you can see that this form now relates to that form right there. I'll have a different amplitude. And you're going to see that I'm going to get the appropriate phase in this equation. That's why we do that. Because I'm going from differential equations to a linear circuit. It's a linear in omega, right? It's a linear in omega, so it's frequency dependent. But we assume that if it's steady state, the frequency does not change. And if it does not change, then you'll see here that omega t term will then put in by hand. So one more time, because I think this is crucial here, so that you have some physical understanding of where we're going. So this term will not change. So it's a constant. So what we're going to do here is that we're going to only focus on the phasor, and then what we do here is we take this term and we put it in by hand at the end. And so that it makes the calculations move very, very quickly this way. So that's where we're headed. So the question is now, how do I get to a phasor circle? How does one get a phasor circuit? And the answer is we need to transform RLC into phasor form. Oops. That's what we started doing last time. Yes, sir.
Is it the e to the j omega t, that's a constant, or the e to the j theta is a constant?
This e to the j omega t will be a constant.
Okay.
So, and as soon as we start to do the calculation, you'll see why I make that statement. Okay? So I'd say just hold on a quick second. As soon as I do R, L, and C, you'll see that that omega term always drops out, and we have to hand put it back into the solution. Yes? Okay. So here's where we were last time. So what we did here is that to do this, I need to convert these guys, transform them into phasor form. So the idea is go something like this. So my process is to think in terms of Ohm's law. And the way I'm going to do that, even though I know this is not technically correct, I'm going to say, I don't care, and I'm going to use it anyways just because it's simple. At least for two of the three circuits that we're going to be looking at. Okay, so this is what we did last time. We started with a resistor circuit. So what I do here is that in order to get into a phasor form, what I do here is that I start with the time domain circuit. Okay? How do I start with the time domain circuit here? So if I have a circuit that looks like this, for example, here's my source. It has an amplitude, and my source is cosine omega t. So I do plus or minus. I have a resistor, and we know that this is the circuit right here. So now what I do here is that I need to transform into the complex plane. And the way I do that is I assume a solution that's complex. So now what we do here is that we assume complex solution. And what's the form of the complex solution? Like this. Okay, so what I'm seeing here is that, note, look at the cosine omega t. Note that it has no phase. So what's the phase angle for this thing? 0. It's not there. So what do I write? I now write my source here. Look how I'm writing it now. I now have a complex source, and it looks like this: Vm e to the j, in this case, omega t. Right? So if I take the real part of this complex source here, I get Vm cosine omega t. I haven't done anything. Right? But I'm moving into the complex plane. So now, here's my source here, and then my resistor here. What we're going to assume here, it has a current IR that's also complex. How does this complex look like? It should be what? IR times E j omega t. And of course, this is my voltage right here. So, no, there's no theta here because this doesn't have a theta. That doesn't have a theta, that doesn't have a theta. In other words, the current must behave like the voltage source. So now, what am I going to do? I'm going to apply Ohm's law. So from here, I apply Ohm's law. And when I get Ohm's law, if I want to solve for the current, I got to get this here. So according to this, the voltage source must be the same as the resistance drop, right? They're both, that's the only thing we see here. So now I look at this guy. This has to be what? IR times R. So here we go. So if these guys are the same, then I could say that the magnitude of this guy must be exactly the same magnitude of that guy. So I'm just going to call it VR. Here, so I should say it like this. So V source is e to the j omega t, which is the same as VR ej to the omega t. And this guy has to be IR ej to omega t times R. So all I want you to do here is that I want you to focus on this. So remember what I said about the omega t term. The omega t term does what? It always drops out. So you can see right here, focusing on this, that drops out. And so when I look at this, so then that means here that VR times IR, if I look at the units of this guy here, it should have units of resistance, as expected, right? So if I look at this here, what we do in phasor form, we typically call it X. And X stands for reactance. And the question is, what do I mean by reactance? It means, how does the resistor behave when I have a source that's constantly changing as a function of time? And what this is telling me here, the fact that when I look at this guy, and this guy is R, note that this has no omega dependence. Okay? And another thing that you don't see here is that note that there is no phase. So let's look at this a little bit more detail. So the first thing here we should say is that we're going to ask the question about phase. The fact that there is no minus sign or no J value. Okay, remember those are important. And just to remind you here that if I have J, I can write this as J to the 90 degrees. If I have a minus 1, I could write this as J to 180 degrees. So the fact that I don't have any J values, the fact that I don't have any minus values, this implies here that the phase between VR and IR is 0. that means the resistive phase is 0 degrees. So when I look at this thing here, what this really tells me here is that VR and IR, that says that VR and IR are in phase. That means that if I have a resistor here, and I look at the voltage source, okay? So I look at the voltage source and it says it's oscillating with this frequency omega. So then I come in here, and you can imagine here is that it's oscillating like this here. And as it's oscillating that voltage across that element, let's call that VR, the current, because it has a phase of 0, right? There's no J value, there's no minus sign, implies that it's going to oscillate at the exact same frequency. Oh, I'm getting out of phase now. This stuff is not sweet. Drop. That's what I mean by that. So when I look at my phasor vector in the complex plane, it says this. So if I now look at XR as a function of omega, XR is exactly along this axis right here. Why? Because the phase of the resistor is 0 degrees. Right? So in the complex plane, when I should not have written it like that. I should have written it like this, excuse me. In the complex plane, that's what I mean, what this vector x of r is telling me. And the other thing that we should say here is that let's talk about the magnitude. The magnitude here says that VR over IR, that this R here is a constant. And what I mean by a constant here is that, like I said, no omega dependence. And so when I look at no omega dependence, if I was to plot x of r as a function of frequency, we would see that this guy is now a constant. So that's what I mean by a resistant element. So in an AC circuit, if a circuit has an angle that's very close to 0, we say that it's resistive in nature. And if it's resistive in nature, that means that these two guys must be in phase, or very close to in phase, excuse me. Let's look at the inductor. Okay, am I too far down over here for you guys? Like about right here? Would that be okay? Remember, this is a new room for me, so about right here? What about you guys? Can you guys see okay right here? How far can I go? About right here? Right? Farther? Okay. You know, if you're not going to say anything to me, I'm going to go all the way to the end.
Carlos?
Yes.
Do those monitors go down
Let's not bring up the goddamn monitor. You know, when they asked for goddamn input when they were doing these rooms, and we said, do not block the whiteboards. What do? This is what they do. They put, you can have this thing all the way. Shit. Why even ask for it? Recommend, advice. Well, we won't go there. So what I'd like to do then is that let's go to the inductor here. Okay? So now let's look at the inductor resistor. The inductor circuit. So when you look at this inductive circuit here, here's what we have. I'm going to do the exact same thing now. So I'm going to have what? I'm going to have a source with an amplitude cosine omega t. Now I have my inductor here. And so what we typically think about in an inductor here is we talk about the current IL. So now, what am I going to do? I'm going to assume a complex solution, like we already talked about. Okay, so now instead of saying I'm going to assume a complex solution, I'm going to say I'm going to map it to the complex plane. Okay, so now I have a complex solution. Right, and so now what I do here is that I look at this guy, and I can see here that this is going to be Vn e to the j omega t. And so we assume here that now I have a complex current. And then I have a voltage that's going to be complex in form. So what do I want to do? I want to get to Ohm's law. So I'm going to use Ohm's law thinking here. So when I look at this current here coming in here, I know that the source voltage must be the same as the inductor voltage, but we already know that this inductor voltage and current are directly proportional to each other in terms of the derivative term. So now, what you're seeing here is that note that the magnitudes of these guys are the same, so therefore the phase that they're actually working at must be the same. So I'm going to call this VL e to the j omega t. This guy will be L. Now, again, I assume complex solution here. So then I go dt, then I go IL e to the j omega t here. Now, you can see that there's something different because now I got to take the derivative and it's going to bring down that j term right there. So when I do that, I'm going to get j omega L, IL e to the j omega t, and once again here, you can see that this guy drops out. And then if I put it into Ohm's law form again, right, thinking Ohm's law, what we find here is that VL over IL has to equal j omega L. And so immediately what you're seeing here is that remember that the units of voltage over current here have to have units of ohms. So that means that this guy has a very resistive type, behavior here. So what they do here is that they define this as XL. Where XL, of course, from what we talked in lab, must be this here. So we got to be really careful here. So XL has units of resistance, but of course it does not dissipate heat. Right? It's not a heating element. It's not resistant because, in 4B, we probably talked about this in this course. Resistors, they dissipate heat. Inductors do not dissipate heat. So what they do here is that they impede the flow of current by the back EMF. The higher the frequency, the larger the EMF, opposing that change, and so that's how it impedes the current. It's not resistive in nature, it's impeding it by the back EMF voltage. Yes?
So then, would that energy be dissipated in the magnetic field or into the electric field?
Or maybe you could say it's being stored in the magnetic field. Okay, so when you're looking at this guy here, what you're finding here is that we need to go back and start looking at the same things. So let's talk about phase. What does phase do? So when you look at this guy, we have this guy that we're really paying attention to. So what you're seeing here, so when I look at X, excuse me, when I look at VL over IL, you see that I get this J term. And anytime I see that J term, I gotta do what? I gotta put it into phasor form. So J is equal to E to the J 90 degrees, because remember, according to Euler's relationship, it looks like this. Cosine goes to 0, sine of 90 is 1, so I write it like this. So the key thing to remember here, in the language of phase, I'm getting VL over IL is equal to E to the plus J 90 degrees. And that plus has a very unique feature here. That plus tells us here is that the voltage leads the current by 90 degrees. Now, I think that's a really remarkable feature. Right? I'm not going to go into this too conceptually, but damn, this is really kind of shocking if you think about it. Because what do I mean by shocking here? Let's look at a resistor. Okay? So to give a comparison here, imagine that we have a resistor. And here's my resistor R. So if I have a voltage source, right, across the resistor, we know that the current or the voltage across that must be the same as the source here. So if I'm looking at this guy, here's my source. So as my source is kind of going like this here, it looks like this. And if I look at the current through this resistor, what happens here is that as I approach this resistor and it interacts with this resistor here, it's like nothing happened, right? They're in phase. The current is in phase here. That's what I mean by a phase angle of 0. But with the inductor, it's different, right? With the inductor, it's really different. And what you're seeing here is that with the inductor, now remember, I'm thinking this is a point. Okay, so I'm not really trying to talk about, I don't want to talk about what's going on in there, otherwise we won't get into circuit solving. And so what you're seeing here is that, look again, the voltage of the inductor is the same as the source. So this guy is coming in like this here. Remember, once again, I'm thinking this as a point inductor here. So I'm not going to worry about what's going on inside. But as soon as, what happens here is that as soon as it hits this inductor, the current is now out of phase. How much is it out of phase by? 90 degrees. And as a consequence, what we say here, by the way, I should have written this as IL. There is now a phase difference. And that phase difference is where? It's along the whole branch where the inductor's at. So I didn't want to sort of like draw it in, but I'll do the dashed lines. But I'm thinking about the first time it's coming in, there's this out of phase guy here. So when I go into the complex plane, so now if I look at the complex plane, and I'm looking at what that inductor looks like, well, you can see if it's J, that J comes in because of this 90 degrees. So when I'm looking at this inductor here, that means that the reactance is at an angle of 90 degrees here. Whereas the resistor is where? The resistor lives in here, and that's at 0 degrees. That's that's what that J implies. So then if I look at the magnitude of this thing, what we're seeing here with the magnitude, just like we saw in lab, we saw that the magnitude of L was omega L, and when we plot this guy as a function of frequency, what we see here is that there's this linear behavior of this guy. And what we talked about in lab here is, and just like we briefly talked about, that at higher frequencies, you're creating a larger back EMF. And if that back EMF is large enough, what's it going to do? It's literally going to do what? It's going to stop the current. It's going to behave like an open. So what you're seeing here, like we saw in lab at low frequencies, we saw that XL is roughly 0, and so it acts like a short. But at high frequencies, you'll see that XL is very, very large. And when that is the case here, we say that it acts like an open. And that's because the back EMF is so large. So any time I deal with the phasor vector, what am I going to do? I'm going to come in by hand, and I'm going to put in this JXL term. So a phasor circuit that now looks like this here, I would literally come in, and I would draw it like this here. So now, my phasor circuit is that every time I see an inductor, I now convert it into this guy, and I start solving problems like this. So now it's linear in omega, and if omega is fixed, then that means I can start solving them, using standard techniques that we used in the past. So now I'll go to the capacitive circuit. Yes, sir.
The VOIO graph, the angle looks like 180.
It sure does look like 180. It should be out of phase by 90 degrees. You're absolutely right. So I should have started like right here. So I drew that out of 90 degrees. I should have drawn it as 90 degrees. So that is a typo. Right, so if I was to really draw this correctly, it should have started right here. So if it starts right here, then it should have been like this. Oops, I'm getting that wrong. But it's got to be off by this factor here. Where the peaks from here to here is 90 degrees. The way I drew that is definitely incorrect. So note, this has a phase angle of 180 degrees. So that is not valid. So let's go to the capacitive circuit now. So I want to do the exact same thing that I did with the, by the way, just to make sure that we're speaking the same language here. This term right here is what they refer to as E line. And you may remember that for 4B. In the old days, they used to symbolize voltage sources with the symbol E. That's where that E line, from my understanding. So it's just this acronym to try to remember, but I don't know if it's worth it or not. So I'm going to do the exact same thing for a capacitive circuit. So if I have a capacitive circuit here, what am I going to do here? I'm going to have some source. I'm going to use a current source this time, and it has some amplitude. Right? I don't have to just have voltage sources. I could imagine that I have current sources. And then I'm going to have a capacitor here. Right, so this guy has to have the same voltage here, and then the current in this circuit should be IC. So I could play the same game. So now what am I going to do here? I'm going to go downwards this time. So now I'm going to go into my phasor solution. So if I look at my phasor solution then, I'm going to replace this with I m e j omega t. And then my current here that's going to be flowing is then going to be IC. That looks like that. And I have some voltage drop across this. So clearly, the current of the current source must be exactly the same as the current of the capacitor. So I guess if I could think of KCL, right, the current of the source must equal the current of the capacitor. It has to be identical. But wait a minute, what do we know about the current of the capacitor? It's related to the voltage of the capacitor. But the voltage should also have a solution of this form. So if I look at this guy then, I could then write that this is going to be C, and I'm going to take the derivative of the voltage of the capacitor of J omega t here. Vc is of course constant because it's just an amplitude. So if I pull this guy out here, it's going to be what? I'm going to take the derivative of this guy, which will be J omega c, Vc e to the J omega t here. Then I get Ic e to the J omega t. Once again, what am I seeing? Cancellations of the omega t. So there's no reason why we should ever think about the omega terms now. So if I do that, what do I want? I want Ohm's law form. If I do Ohm's law, it should be what? Vc Ic equals J omega c. So you can see it's now in the denominator. So now what do I got to do? I'm going to define this as minus J xc. Now the question is, how did I get the minus sign? So if I just do a quick aside here, note that if I have J in the denominator, I can also multiply J star, right? So I could multiply J times J, it's still 1. So then it brings it up and I get minus J. That's where I get that minus J. So that means here, say that again. So J times, I mean this is 1, right? We agree, right? So if I multiply that out, it's minus 1. I get minus J. So where xc here is then omega c in the denominator. So what am I going to do? I'm going to follow the exact same path. So you can see that there's something different here. Look at this phase. Instead of being J, it's got to be what? Minus 90 degrees when I go to do that. So if I follow this type of thinking right here, right? The phase, so now I get what? I get Vc, Ic is then going to be minus J xc here. So if I write minus J in phasor form, it's going to look like what? If that's 90 degrees, this has to be minus J 90, which then is cosine of minus 90 plus J sine of minus 90. And as you already know, sine of minus 90 is minus 90. I mean, it's minus 1. So this term is 0, and I get, of course, minus j here. So if I look at this whole thing here, what this says here is that, look at this picture. So if I look at this picture, what this tells me here is that VC over IC is equal to, as far as phase is concerned, it's going to be J of minus 90 degrees. That minus sign says something very clear here. I can interpret it one of two ways. The way I can interpret it here is that VC is behind the current by 90 degrees, or you can rewrite it. Or you could write this as IC over VC, and then I get plus J 90 degrees. And what does that plus sign mean? It means that this guy is ahead of that guy by a phase of 90 degrees. So either way, I can look at it this way or look at it that way, but what this says here is that the current leads the voltage by 90 degrees. And this is where that phrase is now known as ICE. The current of the capacitor leads the voltage of the capacitor. Okay, so when I look at my curve here, I got to be very careful. Let's see how I do this. So when I look at this guy here, I'm going to have my voltage here. So let me draw the current first. Okay, I'm going to get this screwed up here. So I can only do like a few turns, and then, so let's say that's the current. So that means if that's the current, then the voltage has to lag by 90 degrees. So that means I'm starting here, and I got to go here, and then, nope, right at the, you got to be at the opposite ends here. And then it peaks here. So then when I look at this guy, which is VC, I could see that the distance between these two peaks here is 90 degrees. So in other words, the current leads the voltage by 90 degrees here. So when I look at that angle, what does that angle mean? Well, relative to the complex plane here, this guy is J. If I get an angle of minus 90 degrees here, then that means that this vector has to point in this direction here, the negative 90 degrees. So this angle here is 90 here. So in the complex plane, that's what that vector looks like. And then the last thing that we'll look at here is that the magnitude, if I look at the magnitude of this guy here, we could see here that XC is 1 over omega C. So if you look at this guy here, if I plot this as a function of frequency, you can see that the impedance here, or the reactance, is very large at high frequencies and very low at low frequencies. So when I look at this guy here, it says that at high frequencies, it acts like a short, because it effectively has zero resistance, if I could say that. But it has zero reactance. But over here, it has, at low frequencies, it acts like an open. Now let's be very careful about how I use my language here. So when I look at this guy here, if I have zero frequency, that means that the capacitor is allowed to charge up. And if it charges up, then the branch where the capacitor is at has zero current. if I increase the frequency in such a way that I never allow current to flow onto the plates, then there's no voltage drop across the plates. And if there's no voltage drop across the plates, that means that it has a voltage of 0, so therefore it does nothing. So remember, when I talk about here, capacitors do not dissipate heat. Like resistors, right? They do not dissipate heat. It's called reactance. It's how the reactance is what they do here. They react to the frequency. So if I want a phasor now, so if I now want to do the last thing here, so now in phasor form, that means that every time I see a capacitor, I literally replace the capacitor with minus j xc. Okay, that's it. Now, you know everything now. Okay, so all I've done here is by replacing the resistor with the resistor, replacing the inductor with the JXL, and a capacitor with minus, JXC, they're nonlinear circuits. Dude, as far as I'm concerned, business is done. You know what to do. So what do I got to do? I just got to show you the mathematical tricks. Everything, you know everything. You're going to see it's a pain in the ass. Yeah, phasors. There's a reason why you don't calculate phasors in 4B. You could say, I know somebody who said, oh, we did phasors. I said, no, you didn't. You kind of wrote this on the board and then you were done with it. Watch, you'll see what. Let's go do it. So all I'm going to do now is I'm just going to do example after example. Okay? Nothing is new here. I promise you, nothing is new. Okay? Nothing is new. So here we go. So now, a phasor circuit is linear, which implies here that we do the following thing. There's something called the impedance, which is the total resistance. And when I calculate the total resistance, we typically define that as Z. And when we look at Z, it's going to be R plus JX. Or we can write this as Z angle theta, where Z is R squared plus X squared square root, and theta is the tan inverse of X over R. Okay? And we now have Ohm's law. Okay? I technically shouldn't call it Ohm's law, I still do. And when you look at Ohm's law, how do I write Ohm's law? Do I really got to tell you? What's unsettling is I got a vector, and I got another vector, and I got another vector. Right? Is that a dot product? No. Is that a cross product? No. It's just multiplication of complex exponentials. That's all it is. Okay, I mean, what should I say about here? How about series and parallel impedances? So, what do I mean by series? Add them. What do I mean by parallel? I should be putting vectors here. Let's see, you know what I would say here? We're among friends, so we won't do it. Right? We know we're dealing with complex vectors. Right? Should I write node in mesh? You know what to do. Right? You totally know what to do. So, let's start doing it. Let's look at the first example. Okay? Now, one of your problems that you're going to be seeing here is that you're going to have to worry about sort of like okay. Yeah, I can't load this anymore. Okay, so look at this. You want to calculate the equivalent impedance at a frequency of 10 kilohertz for this circuit right here. Let's just do it. So ultimately, what we want to do here is that we want to get into what? Phasor form. We want it in phasor form. So if I look at my circuit here, I know that the frequency of this system is at 10 kilohertz. And so what I have here is that I got this guy. Right, so this is 1 microfarad, this is 160 microhenries, and this guy's 36. And I know what we're looking at for here is we're looking for this guy right here. Okay, that's what we're looking for. So what do I got to do? I got to make it into phasor form. I mean, you know how to add these, right? It's just 3 vectors in parallel. So what am I going to do? The sum of these is going to be what? The sum of the inverses, 1, 2, 3, and then I invert the whole thing to get the equivalent, right? So first thing I'm going to do here is that I want to go where? I want to go into phasor form. So if I go into phasor form, the resistor stays like the resistor, right? So I have this resistor value. The capacitor looks like what? It's got to be minus J XC, and the inductor has to be plus J XL. So there's the hard way to do these things, and then there's the easier way to do these things. I prefer to do them the easier way, but maybe, I don't know if we should do it the hard way right away. But the first thing that we should probably do here is that we probably want to calculate what XC is and what XL is. So let's calculate this thing. So if I look at XC, it's got to be what? 1 over omega C. And if I calculate this guy, it's got to be what? It's got to be, if omega is what? 2 pi frequency times C. So then if I start to put in my numbers here, I'm going to get 2 pi. Now what I start to do is that I don't typically write in 10,000, I'll do 10 to the 4th. And it's to your benefit to start thinking in language of powers, not freaking numbers. Right? So then if I look at the capacitance here, you can see that that's 1 micro, so then it's got to be what? 10 to the negative 6 over 1. And this has to have units of omega. So if I punch this into my calculator, what am I going to get? Well, you're going to see that there's some rounding issues that we're going to have. We're going to disagree depending on how much rounding goes on. But I end up calculating, just to make sure here, I get 15.915. And I would immediately approximate that to 16. So that's 16 ohms. Right? So I'm going to get XC to be 16 ohms. What does that resistance mean? What does 16 ohms mean? Am I dissipating heat? No. Even though it has units of resistance, I'm not dissipating heat. what I'm doing here is that the capacitor is reacting. And just look at that frequency. Would you say that's a high frequency or a low frequency? I would say that's high, and if it's high, I got to really see how this inductor behaves. But if this is a high enough frequency, I would expect that this guy's getting smaller and smaller and smaller. So now, if I look at XL, XL is omega L, of course. So if I start punching in these numbers here, I'm going to get 10 to the 4th, the inductor here. So now let's look at the inductor. So you're going to have to watch me because I've been talking a little bit too much lately. So my head is kind of not on right. So let's see here. 10 to the 6. This is 160. That's 1.6 times 10 to the 2. So it should be 1.6 times 10 to the negative 4. Right? So I would write this as 1.6 times 10 to the negative 4. Is that right? Okay. So look at the nice feature here of doing that. These guys then cancel each other out. So in my calculator, I just multiply that. And when I multiply this, I get 26.7 ohms for the inductor. Okay, for the inductor. So, well, look at this. This has higher frequency. Higher frequency, I would probably think that the inductor. Say that one more time.
It's like 10.5.
When you multiply that, you get 10? I do get 10. Sorry about that. I do get 10. I'm already looking at the solution. I do get 10. So now, here's this. Okay, here we go. So now, here we go. In phasor form, what does it look like? I have 36 ohms. And I have a cap that has what? Minus J 16. And then I have plus J 10 here. So what I want to do now is that I want to do this. How would you add these things? Well, how would I add them? I'd go something like this here. What I'd probably do here is that I'd probably connect these guys together first. What happens if I have two resistors in parallel? I could then do what? It's the sum of these guys, right? So if I look at if I multiply these two together, I'm going to get what? Minus JXC times JXL minus J times J is 1. So I'm going to get XC times XJ divided by the sum of these two. Right? If I sum these two, then it's going to be minus JXC plus JXL. I haven't done anything different. Okay, so I combine these two here. So when I look at this, what I really did is that I did this here. And then I have this block here. And this block, let's call this guy, how about ZA. Okay, I'm going to call that ZA. So what does ZA do? Well, ZA here, if I just bring this up here, is then going to be what? It's going to be 16 times 36, not 36. 10 divided by minus J16 plus J10. Right? All I'm doing is just parallel. Nothing's changed here. So when I look at this, you can see that this is what? 160 divided by these two here, which will be minus J6. Now note, I cannot have a j in the denominator, so what do I gotta do? I gotta multiply that guy out. J over j. And if I multiply that out, you can see that this guy cancels out that j, and then I get 160. So then I'm going to get 160j divided by 6. And that's what CA is. No, not negative 6. If I get minus j times j is 1, now I have a positive j out. So you can see that the fact that this is positive tells you that the combination of them should have a positive phase if I look at that. So now, what am I going to do next? So now, I'm going to do these two now. If I do these two, what do? Well, that guy has to be what? 36 times ZA divided by 36 plus ZA, and I'll call this ZB. So if I do that, then all I got to do is that I just got to make that calculation. So I'm going to put this into this form here. So then this tells me that this has to be 36 times what? 160j divided by 6 over 36 plus 160 over 6 times j. Are you with me so far? It's just series and parallel. I mean, it's just parallel thinking. So now, if I look at this multiplication, I get 36 divided by 6 gives me 6. 6 times 160, what is that? 1060? I have no idea. Is it 960? Yes, it's 960. I think it's 960. Correct me if I'm making mistakes, please. So then I just got this mess here. So how do I deal with this mess? So note that this is not in polar form. We want it in polar form. But technically, if we wanted to stick to rectangular form, what would I do? I multiply by the complex conjugate to get it upstairs here. So, here's what I'm going to do here. Check this out. I'm going to go 36 plus 160 over 6j times the complex conjugate up and above. I'm going to go 36 minus j 160 over 6 divided by 36 minus j 160 over 6. Okay, this is nasty as hell, isn't it? This is real nasty. So if you're sticking to rectangular coordinates, which is what I'm trying to tell you not to do, this is the kind of crap you got to do. I mean, you know what I would do? I would have punched this into my calculator, and this is what I would have got. So this would have given me ZB. So then Z equivalent must be what? The equivalent of these guys must be this ZB. And if you calculate this guy, you end up with something that looks like this. 21.5 with a phase angle of 53.4 degrees. Now, how the hell do I get that answer? Let's drop this crap here. What I'm trying to show you here is that if you have a calculator, which I know you do, you can actually put this into rectangular coordinates and pop this guy out like this. Okay? This is where people go to Costco and buy one of the calculators and put it in ceramic. For this reason right here. Okay? So, how would I calculate this thing? Not this way. I mean, this is the absolute worst possible way you could imagine. So I know with the 83, the 84, these can totally do it. Okay? So how would I do this? Here's the way I would do it. I was trying to do this to kind of make my point that Phasor calculations are no joke. And this is the worst freaking way you can do it. So how do we do this? We put it into polar form right away. Okay? I only did that to help so that you could see what I meant by you deal with things in parallel just like you did before. So what would I do? I'd go like this. And then I have what? 1, here's this guy right here, so then I'm going to write what? 1 over minus j16 plus j10, like that. So you could do one of two things here. You could enter into calculator in rectangular coordinates. And I'm pretty sure that if you don't know how to do that, you're going to find out real quick, right? Because then you got that crap over there. So that's the way you would do that. If I was to do this in polar form, how would I write this in polar form? Well, let's just keep thinking. Remember, no j's in the bottom, so I'm going to take these j's up to the top. Okay? What's this in polar form? In polar form here, I then get 1 over 36. The j comes up, so it becomes positive j of 1 over 16. And this guy, when it comes up, is minus j of 1 over 10. Put it into polar form. In polar form here, this guy then, so I can add these guys together. And if I add these guys together, I really get what? 36, and then I'm just going to, looks like this guy's going to be bigger. So therefore I'm going to write minus j of 1 over 10 minus 16. Did I do that right? Yes. So then what we can do here is that write it into polar form. So this is the way I would do it in a calculator. Okay? If you're going like, man, I don't know how to do this. Well, here's what we do. In polar form here, what do I get? I get the magnitude. So what am I going to call this is magnitude? I'm going to say that this is, I don't know, let's call it about z. That looks pretty good. So if I look at z here, the magnitude is going to be what? The real part squared, the imaginary part squared, square root. So then I come in and I write 1 over 36 squared times 1 over 10, 16 squared, square root. And then what do I do? I get the angle. The angle is going to be what? It's going to be the imaginary part, which will be minus 1 over 10 minus 16 over 36. And so when I get that form, what do I get? What I get here is that I now have a vector that looks like this. That's then going to look like what? Z e to the j theta. So I want the equivalence. What's the equivalence? So then z equivalent is then going to be 1 over z e to the j theta, which is 1 over z e to the minus j theta. And that will give me my equivalent value right here. So when I calculate these guys here, okay, so when I calculate these guys, I should have put in the numbers, which I didn't. I got, oh man, I didn't reverse it, did I? Okay. It's got to be the reverse of the number here. So I ended up getting this number, 1 over 21.5. And I got this angle here is going to be minus 53.4 degrees. So if I punch this into here, you're going to see here that Z equivalent is then going to be 21.5 ohms with an angle of 53.4 degrees. And that's the answer that I get. So what I did here is that I didn't go through the traditional way of adding vectors, things in parallel. I went through this sort of like mathematically. It says, get it into polar form. Once I get into polar form, I get it into this form right here. Let's go to the next one. I'm just going to keep trying to sort of like keep hitting you with example after example so you can see that you know everything. You know how to calculate everything. The only thing that's going to be the issue here is the mathematics. It's this crap that I got to get through you. Okay? It's not that much different. The problem is you're what? It's freaking finals week. You're saturated like hell. And I'm trying to squeeze in that little tiny bit right into that head, which is not a very good bet. Not a very good bet, but I got to do it. Okay? Let's go to the next one. Yes, sir.
The negative angle, does it go positive because of negative j theta?
Yes. It goes positive because I got negative j, and that negative j cancels out. Okay? Let's look at this circuit right here. Here's this circuit right here. Look what I want to do. I want to calculate the current. How do I calculate the current? Well, one, I could set up a differential equation to solve this problem. Or I could go into a Phasor form, solve a linear problem, and then transform back. So let's do that. So here, let's go to example 10.3.